I guess while we wait for a few more people to join, just in case you didn't see the campus wire messages, the recording servers for Zoom have been overloaded recently, so it's taking a while to process some of the videos. So in the case of the seminar, we actually did have a separate recording through QuickTime that we could upload immediately, but there's going to be a delay for the actual videos from Zoom, but we should eventually be able to upload them. And so I think that was the case for yesterday's videos. Okay, yeah, it looks like we have 45 participants, so we can go ahead and get started. Okay, so in this lab, again, just accessing it, it's through this day 3. And it's this mask LM lab, and then we're looking at this masked LM's notebook. Let me just turn off this sidebar to give us more space. And the so the lab today is going to be over this BERT model that was mentioned in the lecture earlier today. And in order to explain BERT, we're going to take a close look at this masked language modeling. And then also do a review of transformers along the way. Okay, so the background, again, we're going to go over this BERT model. Here's the original paper for BERT, if you're curious to go read. And BERT is actually, excuse me, an acronym, which stands for Bidirectional Encoder Representations from Transformers. And so actually all those things have significance, and hopefully if you haven't already seen it from the lectures, then you'll get some additional understanding of those from the lab today. Why we say, for example, bidirectional, you might be able to guess why transformers is in here. And so the goal of BERT is, or how it's commonly used, is that we're going to pre-train some large-scale model, and that model will give us some language representations. So by representations, literally, I guess we mean some vectors. And then step 2 is going to be, we'll fine-tune that model on some downstream task, like, for instance, question answering, summarization. There's a whole suite of tasks that were actually mentioned earlier. There's these glue tasks and super glue tasks. So you can get creative with the different tasks that you use this model for after this pre-training phase. And the pre-training phase is going to use this objective, which we call undirected, or the model is undirected, but we call the language modeling objective masked language modeling. And it's going to work as follows. So we're going to randomly mask some tokens in the input, and then the goal is going to be to predict the original vocab ID. Okay, so here we're given some sequence. This will be from a data set, so some sentence, for example. And then we're going to form this mask where it's either 0 or it is 1. And 1 means that the token will be masked. And so, for instance, we'll look at details below. You could imagine masking out, for instance, 15% of tokens at random. Okay, so now you're going to have this new input where some of the tokens are the original tokens, and some are this mask token. So this new input sequence. And then here's the loss function that you'll use. This is summing over each masked position and then taking the log probability of the true token given the entire masked sequence. So when you think about this in terms of a network, and we'll see this below, you could think about giving this masked sequence as input to the network, and then looking at the positions that correspond to masked positions and seeing what is the probability of the true token in that position. So that's how you can form a loss function for this masked language modeling. Okay, so we'll see this concretely below. I thought maybe we would just mention it up front, but now we're going to actually go into a review of the transformers, because part of BERT, if you remember, is that we're using this transformer architecture. Okay, so transformers, we've seen a couple times over the previous day. And I guess to motivate them, we could think about first what we did with recurrent neural networks. So with recurrent neural networks, when we were just doing normal language modeling, we had these different conditional distributions, and we had this hidden state, which was kind of recursively defined in the sense that, you know, you have some hidden state, you produce a new one, and you kind of go in this process. An alternative is this transformer architecture, where you could sort of think of it as this being some kind of feed-forward computation instead of this recursive computation. And again, we'll see this concretely below, so hopefully these intuitions aren't too confusing. And in this case, you could compute these different conditional distributions as follows. You could view this transformer as just being some function which takes in an input and produces a sequence of hidden states. And then each conditional distribution is taking the hidden state for that position and transforming it and taking the softmax. Okay. So now to go into details, how we're going to use this for masked language modeling is actually simpler than maybe what we were doing in the case of translation. For masked language modeling, we're not going to have a separate encoder and decoder. We're just going to have this single transformer. So you could think of this as, well, I mean, just think of this as being a single model, and there's no separate encoder, say over here. And what is this transformer doing? Just at the highest level, what it's doing is it's receiving some input sequence. So here we can actually see that the input sequence contains this masked token. And then at a high level, it's doing some transformations, some nonlinear transformations. And at the end, you get a vector. And it's one vector per position of the input. Okay, so is this making sense so far? Okay, good. So right now we're just viewing this as some kind of black box, which gives us some vectors, given some input sequence. And so now we could actually review what operations is this transformer doing. And I guess I'll pause throughout, but I'll assume that it's helpful to kind of go through this slowly, the different operations that it's doing, because I think it'll be a good review. But if you want me to skip some parts, just let me know. Okay, so the first key idea in transformers is these position embeddings. Okay, so unlike the RNN, which had some notion of different time steps determined by the hidden state, this transformer is going to not have a sequential notion. So we actually have to tell it explicitly about positional information. And so positional information, by that I mean that, for instance, the first element of the sequence is in the 0th position, the second is in the 1th position, and so on. So as far as the recurrent, there's a question about the recurrent mechanism. Maybe we could answer that just through the chat, and right now I'll just focus on going over the transformers, which is separate from the recurrent neural networks. Okay, and so the way you're going to do this is to introduce some vector representation of the positional input. So you're literally going to have for each item of the sequence some vector representation of its position. Okay, and then again, you're going to give that as input to the transformer, and you're going to get out some vectors. So we can actually look at this, a concrete example of this. So here is an input sequence. Beginning of sentence, my pet, mask, and this other token. It's actually, they just use the same representation here, actually in BERT for beginning and end of sentence. And let's set some max length of 10. And the reason we'll do that is because if you can imagine having a different embedding vector for every length, then you need to specify some max length. At least with this method of doing position embeddings that's shown here. There's other methods that don't require this max length, but let's just look at this one. Okay, so now we define our vocabulary. We've also called this a dictionary in other parts of the course, which is just mapping a token to some number. Okay, and now we're saying that we want our representation to have 6 dimensions. And you could change this to whatever you want, 64 if you want. And so now we're going to have 2 different embeddings. So one is going to be a token embedding, and that's going to be one embedding per item of the vocab. And then we're going to create a separate embedding, which is for the positions. Okay? And now here what we're going to do is convert the input sequence to a sequence of the numbers. And then we're going to create both embeddings. So here's doing the token embedding, and then here's doing the position embedding, where this is enumerating 0, 1, 2, etc. to the length of the vector, and so on. And then we're just going to add the 2 vectors together. Okay, so the 2 embeddings again. Yes, so if we look at this transformer, what we want to do, what we're trying to figure out is how do we give inputs to the transformer? And I guess as we've seen before is that we create vector representations of the inputs. In the case of the transformer, we want to come up with a vector representation of the token. So that's here. And then we also want to come up with a vector representation of the position of the token. Okay, so then that's here. So does that make sense? Okay. And so then this code is just going through the input sequence, and it's creating these 2 different types of vectors, or 2 different types of embeddings. Okay? And if we look at what we get in the end, we get something which is dimension 5 by 5 by 6. Let's actually take a look at this. So this might actually be incorrect. I think it should be 1 by 5 by 6. Yeah, I'm guessing something's happening incorrectly here with the addition. So let's just debug this real quick. Okay, so it looks like something is happening when we do this addition. let me, sorry about this, but I mean, I guess you're seeing how you would debug this. So this is of size 5, 6. Okay, so we can see that we have to do this unsqueeze here. Now these two dimensions match. Okay, and so now you get something which is length of the sentence, which is 5, right? We had 5 different tokens. And then the batch size, which is just 1. And then our dimension, which up here we specified to be 6. Okay, and so if you look at this, what it's saying is that for each element of the input, for each position, we now have some vector, which we could provide as input to the transformer. Okay, and so this is one way of doing this position embeddings. In the transformer paper, they used another method with these sinusoidal functions. But you know, this is another way of doing it, and it's similar to the way that they're going to use in the BERT model. Okay, so the second key idea, I guess, of these. Okay, so yeah, so then the masking. This is just as a, so remember the goal of this lab is to go over masked language modeling here, where you come up with this modified input sequence that has some of the tokens masked. So this is just showing, kind of looking ahead to this, to later in the lab, when we actually show how to do masked language modeling. This is how your input sequence would look like. Okay, so then the second key idea with this transformers is the idea of this modularity. And what we mean there is that if you look at how it's implemented, it's actually repeating, it's actually repeating the same structure n different times, so multiple different times. And these are referred to as layers or also blocks. And essentially each block in this transformer, you could think of as receiving some input vectors and producing some output vectors. And so at each stage, the block is just going to be kind of transforming the input vectors into the output vectors. And then you just repeat this process. Okay, so that's just at an abstract level, but it's kind of showing how this is structured. Now we can look at what is this doing here? Okay, so now in this case, we're going to actually look at some evidence of this. So we're going to look at this transformer encoder class that's actually implemented in PyTorch. And you can see here that the description is that it's a stack of n encoder layers, which kind of lines up with that diagram. Yeah, I guess that's all this is saying. And so now the next step is to look at the forward pass. So, oh, I see why this is printed out. So this is showing that you could initialize one of these transformer encoder layers, and it's showing how it's used. So now we'll do that below. Okay, so now here we're going to initialize one of these layers. And again, a layer you could think of being as one of these green blocks. And we're going to specify the different parameters. So first of all, you have some dimension, and this will be consistent for the input dimension and the output dimension. You specify a number of attention heads, which we've discussed, but we'll also review again below. And then you specify the dimension for this feed forward transformation, which again we'll review below. And then also you specify this dropout level. Okay, and now if you could just make sure everyone is muted. Looks like Looks like someone needs to mute. Okay. I think I found it. Found the mute button. Okay. So now we actually define this transformer as just being these encoder layers and then picking a number of layers. And you'd pick this based on some performance on a held out validation set. But here we're just going to say 4 because we're just seeing how this works. Now if we're just treating this again, oh, I didn't run this. If we're just treating this as a kind of black box that we haven't looked at the details yet, what does this give us? So we give it some input embeddings, which again, we computed above, and we get some outputs. And so you can see that the input size is matching the output size. And in particular, we're printing out the outputs here, and you can see that we get one different vector for each element of our 5-element sequence. Okay, so this is just concretely showing this diagram. Idea that we give it some input vectors, and then after running through the network, we get some output vectors. And yeah, I guess they're being transformed along the way, so maybe that's why you call it the transformer. Okay, and the parallel is the idea that if you look here, we actually have a sequence of 5 different time steps, but we're just doing a single pass through the whole network. Okay, and you could contrast this with a recurrent network where at each time step, you're having to do some new operation. Okay, so now we can take a closer look at these layers, and they're going to consist of 2 parts. So self-attention and this feed-forward network. And again, we're taking some vectors as input and transforming them into some new vectors as output. Okay, so self-attention. So self-attention is here. So here's a formula for it. And if you remember back, there's kind of 3 different items that are used. So these queries, the keys, and the values. And then how it's going to work is that the queries and the keys are kind of multiplied, and then there's this normalization, which we discussed yesterday. And then by taking the softmax, you get a distribution over the different positions. Then given that distribution, or given that weighting, that will allow you to do a weighted sum of the values. So that's kind of what this equation is saying. It's saying that we're going to compute some weighting using the queries and the keys. And then we're going to use that to take a weighted sum of these values. Okay, there was actually a detailed example here originally, but I guess there's not a full explanation about the attention again here, because I guess at this point, just due to the time, you'll have to just go and review the preceding materials. But we could at least look at, well, we at least have this formula here, and we could at least look at how this is used in the PyTorch. Okay, oh, sorry, and one last thing to say is, like, why are we using this self-attention at all? The key idea is that the output vector at each layer is able to incorporate information from every single input. Okay, so essentially, if you look at, let's consider this vector here. It's saying that since we're using this form of self-attention, this vector can kind of incorporate, or it's a function of, all of the input vectors here. And so if you think about, if you contrast this with a recurrent model, the recurrent model is unable to incorporate information from these future tokens, at least without modifying it. You could modify it to kind of take both directions, but at least conceptually, it's helpful to think about why we're using this, or one way in which the self-attention is useful. And it's that the representation that we get here can incorporate things from both directions. And so that is actually, let me just jump back real quick. That's actually the bidirectional in BERT. It's that these vectors that we're going to get take into account both directions of context. Okay. And so, oh yeah, and so then at each position, you could simultaneously compute the attention from using the preceding inputs. Okay, so let's see, what does it say here? And then, yes, okay, so then this is just showing in PyTorch how it's implemented. So they actually have this multi-head attention class, and then you give it some dimension and some number of heads. And then here, you could define the query, key, and the value as just being the the outputs from the preceding layer. And that's what we mean by self-attention, that this query, the key, and the value are all, like there's no separation between an encoder and a decoder. You're just using the preceding outputs there for all three. And so again, yeah, unfortunately here we won't look at the details of the implementation. But again, you could just view this, if you want for now, as taking in some inputs and transforming them into some new outputs of the same shape. Except now these outputs are going to have incorporated information from all of the inputs. And if you want, I would recommend going through the the lecture slides in the previous lab and really understanding the formulation of self-attention. But if you really want to look at the implementation, which I guess is another thing that's important to maybe understand, you could look at how it's actually implemented in PyTorch using this feature here. Now, I will say, here it's going to be implemented with all these different matrix. I mean, it's not that bad, but it's going to be implemented to ensure that it has good performance. So it's really good to first sit down and maybe understand it away from the code, and then look at how it's implemented. Okay. Yes, and then this feed-forward network, I guess we don't explicitly have a review for that part of it. Okay, so now in summary, you could define one of these transformers as follows here, where you have the two different types of embeddings. You have the encoder, and you have the projection to get the vocab elements at the end. And then the forward pass is going to consist of just forming these embeddings here, and then applying this encoder function. Okay, and if you want, you could go back and kind of correspond all of this with the diagrams to hopefully understand what's going on. Okay, so this will be our transformer. And then this is just showing an example of computing what we'll call features. So these are computing the vectors for a certain input sequence. Okay, so looks like we're about halfway through. So due to time, we do have to keep moving, but maybe I'll pause briefly for questions, or hopefully we're able to answer them in the chat. Okay, so now that we've reviewed transformers, we can go back to this masked language modeling. And as we discussed before, the property is that due to the self-attention, each output vector is going to be able to incorporate information from all of the input tokens. So we might expect this transformer to be a good architecture to use to get these representations that we then use for downstream tasks. And so masked language modeling, again, is going to look like something here, where we mask one of the input tokens, feed it through the network, and take the softmax, and then we get some distribution over that word given the masked input. And that's the masked language modeling problem. And of course, you could have multiple tokens that are masked in the input sense. So here we're going to see how to do this on Persona Chat. Looks like I created a new instance, so I don't have this installed, so I'll do that. So here, this is going to show you how to actually do this on Persona Chat. And then below, we're going to load the actual pre-trained BERT model, which will be much larger scale and much more, I guess, useful for downstream tasks. So here, again, is just standard data loading. Here's what our input sequence, our input batch would look like. This is going to be the time dimension, and then this is going to be the batch dimension. And that's just based on the way that the transformers are implemented. Now, here's the function which will actually mask the input. And here's where, if you want to experiment with different things, you could change the percentage of time that the input is masked. Okay, so so here, this is actually doing exactly what they did in the paper, and it's kind of it's maybe kind of detailed. And so what it does is that 80% of the time you're going to replace the token that was masked with the mask token. So most of the time. And then 10% of the time you're going to replace it, instead of with a mask token, with a random word. And then 10% of the time you're going to actually leave the masked input token unchanged. Now, this is potentially confusing. Why would you want to do all of this instead of just masking the input tokens? It turns out that this is what they did in the original paper, but some subsequent work afterwards, like this Roberta model, for instance, actually did the normal thing, I think, or they might use a different strategy. So maybe don't get too caught up in the details of this 80% and 10%. And maybe just focus on the important thing, which is we start with a batch, and then we're going to mask roughly, say, 15% of the tokens. And then again, if you want, you could consider what do they exactly do. Some of the times you leave it as a mask. Sometimes you change it into a random word, or leave it as it is. Okay, so what does it look like after we do this? You can see now that this mask ID is 1. And now you can see that in our batch, some of the elements have been masked. Okay, so this is just what we'll use for training the model in the setup. And now you could look at what are the labels. So in positions that weren't masked, we're going to ignore those. Remember, because our loss function only sums over the masked locations. And in positions that were masked, so let's look at this one for instance, you have what is the ground truth label there. Okay, so here you can see that the task is to predict the ground truth label and the mask positions. So now we're going to create a transformer. And again, due to this way that we're doing the position encodings, and there are different ways of doing it, but due to the way that we're computing the position encodings, we specify some maximum length. Now you could look at what happens when we feed the inputs, which are here, through the model. And just to make sure we understand what's going on, you can see that you get the sequence length here and the batch size here. And for each element, you're getting it's not a distribution yet because we haven't taken softmax, but you're getting a number for every word in this 19,000 size vocabulary. And then the loss function is going to just be this cross entropy loss, which we've used before. And remember our labels we computed earlier up here. So those are really the key ideas of how you would train the masked language modeling. Of course, if it's the first time you're seeing it, it might, I mean, you might have to go back and review, but really the key ideas are just making this mask and then making sure your labels are correct and using cross entropy loss. So just in the interest of time, again, we won't go through the training loop here in detail. But again, you'll see that it really doesn't differ that much from the training that you've seen before, except that you're doing the step of masking the tokens. Okay. And then, of course, if you want, you could set this to true, and you could train your own model. Okay. So now we're going to, if you were to run this training process using the masked language modeling, here's an example model that you might get. So we're going to load this pre-trained model. And here what we're going to do is just look at different, providing it with different inputs that are masked and looking at its distribution over the masked positions, just to get a sense of if it's learned something on this small data set. Then we'll go to a more realistic task below. Okay, so here again, we have different input sequences. So here's an example sequence. We're going to do a forward pass through the model, take the softmax, and then look at, in each one of these mask positions, we're going to look at what the distribution over tokens is. So that's what this code is doing. Maybe we can actually look at the result and you'll see what it's doing. So while that's running, this if statement here is just, it's just because below we're loading a pre-trained model. We're not training from scratch. So this if statement here is just for convenience, that I didn't accidentally run the cell and it would start training. Okay, so if you were going to train from scratch, you would change this to true, if that's what the question was about. Okay, so let's take a look at this. So here's an example sentence. I have a pet mask. And we could see that it learned, I mean, at least some of them are, the top two are kind of reasonable. So we have cat, and then we have dog. Some are not reasonable, like sibling. But you could see, I mean, this is a very small data set. It's a very small model, relatively speaking. And you could see that it at least learned something kind of reasonable. Here, when we add the word to, you can see that it puts this plural, so cats, there again, and that would have the highest probability. Now, this mask was almost at the end of the sentence. It actually technically wasn't at the end. But again, the difference with this mask language modeling is that this mask could be anywhere in the sentence. So here we're masking out a token early in the sentence. And again, at least the top ranked things are fairly reasonable, such as my mother is a lawyer. And so you could see that in order to determine this, it had to use context from both sides. So that's this bidirectional idea. Now, another thing to understand with this model, and someone actually asked a question about this earlier today, is if we're making two predictions at once, do we do those kind of sequentially or all at once? And it turns out that we do it all at once. And this actually introduces some conditional independence in the sense that when you're going to predict this mask token, you don't know what the value of this one is going to end up being. You don't know what the prediction is going to end up being. You're just predicting both at once. And it looks like when you just have two tokens, it's actually still kind of reasonable. So you could say my mother is A, and then for the second one have teacher or lawyer or something like this. But you could see that when you get to three simultaneous predictions, you can see now what this conditional independence assumption results in. So here it's saying I am, for the top ranked thing, A, comma, sometimes, which doesn't really make sense. If you look at, for example, the second ranked thing, it would put a period. So here you could see that it's not able to take into account the prediction value because you're doing it all at once. And that's maybe just a property of this, the way that we're doing mass language modeling here that is good to understand. Okay, so this kind of explicitly showed how to do the mass language modeling. But in practice, what people do is to, or I mean, what some people do, some people actually have to train these. Common thing is to use an existing library, like this transformers library, and load a pre-trained model. Okay, so here we're going to load the actual original BERT model from the original paper. And I guess we're loading this BERT base, which has 12 layers and about 100 million parameters. If you want, using the same, this wasn't downloaded. If you, okay, so if you want, you could change this to be the large model. And the large model would have 24 layers and 300 million parameters. Okay, so I actually created this new instance since the instance was down yesterday. And on this instance, it isn't downloaded. So let's hope that this downloads quickly. But in the meantime, we can look at what we'll do below. So here is how the actual BERT model is going to represent the inputs. And you'll see that it's kind of similar to what we've done before. Except in this BERT model, they trained it using two sentences at once. Okay, so you're going to have one sentence here, a separator token, another sentence, and a separator token. So in addition to the token and the position embeddings, they also have these kind of segment or sentence embeddings. So here's part A, and here's part B. One reason for this might be that some of the downstream tasks, it's useful to have two sentences. Like you could imagine classifying, taking in a sentence pair and saying, are these two sentences contradictory or do they entail each other? That's an example downstream task. Or question answering, right? So you could have some evidence passage here and some question here. And then you could, for example, classify either an answer or classify a location of where the answer is in the evidence passage. Okay. Now, the text representation in BERT does something a little bit different. So instead of having a token for each, a number for each word, it actually uses something called subwords. Now, subwords, I guess, for this purpose, you could think of running some algorithm on input text, and the algorithm gives you some vocabulary. And the vocabulary might actually represent a single word as two different kind of chunks. So here, for example, this pre-training might end up being represented as a token for pre, and then a token, and then a token for training. And so this allows the model to build up different representations at a granularity that's more fine-grained than just words. Okay, so that's called subwords. Let's see how the download's doing. Okay, so it looks like it'll finish in time. So here, once it finishes, I can show you exactly what the subword thing is doing. But here, I'll describe the task that we're going to actually use this BERT model for today. So again, there's many different tasks you could use BERT for. If you want, you can look up these glue tasks online. But here, we're going to use something which you might call this probe. And a probe is used to investigate some property of a learned model. And so this is from a paper by researchers at Facebook AI Research. And they designed this task to ask the question, what sort of knowledge, like factual knowledge, has this BERT model learned? And specifically what they do is they take this BERT model, which I guess here is represented by these squares. And then they give it some sentence here. And in the sentence, the sort of factual content of the sentence is masked out. Right, so here you're asking a kind of factual question about where this Dante was born. And it turns out that the answer is Florence. And so if you run many different examples like this, you could check how often the network gets this correct. Or maybe a less strict thing you could do is check how often the correct answer is within its top 5 to 10 answers. Because again, we're just looking at this network that was trained with masked language modeling. We could always fine-tune it to improve its performance in a task. But here we're just saying, just due to the masked language modeling, has it actually learned some factual knowledge? Okay, so kind of interesting task. Let's see, okay, and the download's done. So yes, here's an example of the subwords. So here you can see that this pre-training is actually going to be represented as 3 different tokens, right? So pre, tra, and ening. You could ask, like, how does the split come about? Well, again, for the purpose of this lecture, you could just think of there's an algorithm that you can run that will determine splits based on different criterion. And if you want to look into the details, I put a link here of the kind of subword algorithm that's used in BERT. It's called sentence piece. Okay. So let's take a look at this. So here we're just downloading the data set. And let me just kick this off because it takes about, well, just a few seconds. But here's an example from the data set. So to emphasize the 50th anniversary of the Super Bowl, the mask color was used. Oh, I shouldn't have shown the answer. I could have asked, does anyone know, without looking, what the answer is? I guess it's too late. So the answer is gold. And you could see there, arguably, you would have to, yeah, I mean, I guess it's just a fact that you have to know based on this 50th anniversary. You would have to know that they use gold. Okay, and so now here what we're doing is we're just looping over the data set, and we are checking what are the top tokens and what is the correct the accuracy. Oh, oops, I just ran it again. I actually don't watch the Super Bowl either, so there's no way I would have known that. So I have to rely on BERT for my Super Bowl facts. Okay, so it turns out that the correct at 1 is 12%, which might seem kind of low. Actually, here in the code, yeah, so actually a better thing to do would be to check the correct at 5, which means like in the top 5 ranked tokens, how often is the correct one appearing? Because again, we didn't explicitly train the model for this task. We're kind of just saying, did it roughly learn some sort of knowledge? And then here, it's a lot of code, but what it's doing is it's just visualizing different predictions. So here you can actually explore this yourself. Here's choosing an index. Here is choosing an attention layer, which will be visualized below. And then this checkbox here will determine if it's going to show you a correct example or an incorrect example. So let's look at a correct example. So Newton played, it's another Super Bowl question. So Newton played as Mask during Super Bowl 50. And in this case, it got quarterback correct. So just due to this Mask language modeling process done on a large corpus of data, it turns out that it was actually able to correctly predict this quarterback for this Mask location. Okay. I'll have to, I'll defer to the other course instructors for answering the question about what was Newton's first name. Okay, and so this attention layer here, I guess we've seen other visualizations, but here this is showing the fact that at each layer, we're going to have 12 different attention heads. Okay, and then here you could actually see the actual attention heads from BERT. So for instance, yeah, I mean, I guess you could at least see that they're kind of learning different things. And here you might see some structure where it's really focusing on this Newton word. This one seems to focus on the first 2 words. And I mean, maybe you shouldn't spend too much time trying to interpret these, but it's good for at least getting a feel of what's happening here. Another thing you could look at is that at different layers of the network, the attention will have learned different things. So here we're looking at the last layer of the network, and you can see that the attention structure is a lot different. So it looks like actually some of the heads are just focusing on the separator token. Others are having this kind of left to right structure. And there are a couple papers that have tried to identify patterns in these. But at least for the purposes of this lab, I would say maybe just look at these to get some intuition that the heads are learning different things and that it's going to differ based on the layer. So maybe let's look at an incorrect example. Oh, so it actually got this one wrong. So here it said Okay, so the 12 heads is, if you remember, we used this idea called multi-head attention. So the number of heads refers to that multi-head aspect. And each head is going to be computing a kind of separate weighted sum of the values, right? So you could imagine that each head, yeah, I guess this is just talking intuitively, like each head can kind of compute different information in the sense that it's weighting the different values differently. So this one, for example, is contributing to the output by placing most of the weight on this separation token. Whereas this one is kind of contributing by looking at what is the previous token. And then if you want to actually look at what the head actually means mathematically, you should go back and look at the, I guess, the formulation in the slides. So here it looks like it got gold wrong, but you could, I mean, to be fair, again, it wasn't trained explicitly for this knowledge task. So I'm sure if you fine-tune directly on this data set, it would get it correct. You could see that it still learned kind of something reasonable, which is to put a different color name there. And here it is within the top 10. So we have like 3 minutes left. If anyone has any questions. Oh yeah, so these heat maps. So each heat map here is showing, yeah, I guess I didn't explain what these axes are. So the axes are showing each input token, right? So on the left here, we have beginning at this CLS token down to the N token. And then up here, we have the same thing. So now if you look at one of these squares, let's look at this one, for instance. This square is saying, what is the attention score between this input position and this output position? Okay. And the attention score is going to be the kind of weight that is computed for this weighted sum of the values. Okay. Yeah, and so I just want to say here, and I think there's a question about it. Here, again, the purpose of this task was to kind of see what the masked language modeling process sort of resulted in. And you could see that it results in, I guess you could at least say, based on these results, it results in a reasonable ability to get this factual knowledge within the top 10. Okay? Now, if I was going to actually use this for a question answering scenario, I would actually fine-tune this masked language model on this question answering task. And so unfortunately, we don't have time to discuss that fine-tuning in detail, but you could certainly, now that you know about BERT, if you do some reading, you'll certainly see this pop up a lot. This notion of taking BERT, which is fine-tuned, which is pre-trained, and fine-tuning it on some task. And so after fine-tuning, I would expect that, especially in the small data set, the top 1 accuracy would improve substantially. Okay, so that's actually the end. Hopefully this was a good introduction to the masked language modeling, as well as a review of the transformers. And as a kind of researcher or as a practitioner, this idea of using a pre-trained model is something which has come across pretty recently, but something that's very effective. So hopefully this will give you a good base for understanding the future ideas. Okay, thanks.